Welcome! Today, we are diving deep into the physics of the X-ray beam. We're going to take these fundamental principles, the stuff of equations and textbooks, and really transform them into practical, clinical mastery. All right, so here's our game plan. We're going to start with the basic recipe for an X-ray beam, then figure out how we can control it. After that, we'll get into filtering it for patient safety, master the rules of exposure, and finally, put it all together to optimize dose and solve some real-world problems. Let's jump in. So, first things first, what is an X-ray beam actually made of? Well, it turns out it's not just one thing. It's a very specific mix of two different types of radiation that are created in the exact same instant. And here they are. On one hand, you've got Bremsstrahlung radiation, which gives us this broad, continuous range of energies. And on the other, you have characteristic radiation, which creates these really sharp, specific energy spikes. Both of these things are happening at the same time at the anode. And together, they make up the complete X-ray spectrum we work with. Now, this is where most of our X-rays come from. You have a high-speed electron flying from the cathode, and it gets close to the powerful positive nucleus of a tungsten atom. That nucleus pulls on the electron, causing it to swerve and slow down. It's literally braking radiation. That's what Bremsstrahlung means. The energy that the electron loses in that braking action is shot out as an X-ray photon. And because the amount of braking can be a little or a lot, you get this whole continuous spectrum of different X-ray energies. So what's the second ingredient? Well, sometimes that incoming electron acts like a cue ball in a game of pool and just smacks an inner shell electron right out of its orbit. This creates a hole, an empty spot, and the atom becomes unstable. So an electron from a higher energy shell immediately drops down to fill that gap. And when it drops, it releases a very specific amount of energy as an X-ray photon. It's a predictable energy, a characteristic signature of tungsten. But this only happens if you give that incoming electron enough of a kick, at least 69.5 kilovolts of power. So, we have our two ingredients. Now let's talk about the control panel. How do we actually sculpt this beam? Well, it really boils down to two main settings, kVp and MAS. Think of kVp, or kilovoltage peak, as the accelerator pedal. When you increase the kVp, you're giving those electrons more speed and energy. This means you can create higher energy X-ray photons, which shifts that whole graph to the right. But here's the kicker. It also makes the whole process way more efficient. So not only does the beam get more penetrating, but you also get a lot more X-ray photons in total. See how that curve gets both wider and much, much taller? Now, MAS, or milliamperage seconds, is much more straightforward. Think of it as the volume knob. It controls the number of electrons you're sending over to the target. So if you double the MAS, you simply double the number of electrons, and you get double the number of X-ray photons. The curve gets taller, but notice it doesn't shift left or right. It has zero effect on the beam's energy or penetrating power. It is a pure quantity control. Okay, so we've just figured out how to create all of these X-ray photons. But here's the catch. Not all of them are actually useful. In fact, some of them do nothing but harm the patient. And this brings us to a really important idea, filtration. I know, it sounds totally backward, right? We just went through all this effort to generate a powerful beam, and the very next step is to block part of it on purpose? The answer to this gets right to the heart of our guiding principle in medical imaging, ALARA, which stands for as low as reasonably achievable. It's all about patient safety. And here's how it works. We place a thin sheet of aluminum in the beam's path. This aluminum acts like a sieve. It's designed to catch and absorb all the low energy, or soft, X-rays. Why? Because those photons don't have enough punch to make it through the patient to create the image anyway. They would just get absorbed by the skin, adding to the patient's radiation dose for absolutely no benefit. You can see the results so clearly here. On the left, that unfiltered beam is loaded with those useless low-energy photons. Then, on the right, after filtration, they're just gone. We call this hardening the beam, because by removing the softest photons, we've increased the average energy of the beam. It's now a more efficient imaging tool, and we've dramatically cut down on unnecessary dose to the patient. And how do we measure this hardness, or the quality of our beam? We use something called the half-value layer, or HVL. It's pretty simple. It's just the thickness of aluminum it takes to cut the beam's intensity by exactly half. A higher HVL tells you that you have a more penetrating, higher quality, and ultimately safer X-ray beam. Okay, let's take all that physics and boil it down to the essential rules of the road, the core principles that are going to govern every single X-ray exposure you make. First up is the 15% rule. This is such a powerful tool in the clinic. Remember how KVP dramatically affects the beam's intensity? Well, it turns out that just a 15% bump in KVP will have the same effect on your image exposure as completely doubling the MAS. This is huge because it means you can cut your MAS in half, which can slash the patient's radiation dose by 30 to 40%, all while keeping the image looking great. Next is the inverse square law. This is just a fundamental rule of the universe. The intensity of radiation drops off fast as you move away from the source. To put it simply, if you double your distance from the X-ray tube, the radiation you're exposed to falls to just 1/4 of what it was. This is absolutely critical for keeping both the patient and yourself safe. This table just lays it all out perfectly. Look, beam quality, the penetrating power, is really only controlled by two things: KVP and filtration. But beam quantity, the sheer number of photons, is affected by everything. It goes up with MAS, it goes way up with KVP, and it goes way down with distance. If you can keep these relationships straight in your head, you've mastered radiographic technique. So, we have all this theory. How does this actually play out in a hospital or a clinic? Well, the goal is always to follow the ALRA principle, to keep the radiation dose as low as reasonably achievable. And here are the 6 best ways to do that. You can see how the physics we just covered leads directly to these clinical best practices. Using higher KVP and lower MAS, that's our 15% rule in action. Proper filtration, that's hardening the beam. And tight collimation, just shrinking the beam to cover only the part of the body you're interested in, is maybe the simplest, most powerful dose-saving tool we have. All right, for our last section, let's put this knowledge to the test. We're going to take a really common clinical problem and see how understanding the physics helps us figure out what went wrong and how to fix it. Okay, so imagine this scenario. We're using the automatic exposure control, or AEC. That's this system that's supposed to be our autopilot, measuring the radiation and shutting the beam off at the perfect moment to get a great image. But what happens when that autopilot gets confused? What happens when we put a big piece of metal, like a hip implant, right over the detector? Well, the physics tells us exactly what's going to happen. That metal hip is going to absorb almost all the radiation. So the detector underneath it is completely starved for signal. The AEC system, thinking it hasn't gotten enough radiation yet, just keeps the beam on and on and on, probably until the safety backup timer finally kicks in and shuts it down. The result? All the normal tissue around that hip implant gets blasted with radiation and is massively overexposed, looking black on the final image. The key takeaway is that AEC is not magic. You have to be smart about it and select the detectors that are actually under the anatomy you want to see. You know, in the end, mastering these principles isn't just about passing a physics exam. It's about truly understanding the tools you work with so you can adapt to any situation. It's how you provide safer, smarter, and more compassionate care for every single person who comes through your door. The real question isn't just what is an X-ray spectrum, it's how can my understanding of it better serve the patient on the table?